There was something wrong with the video yesterday. After about half an hour, it stopped recording the video and it only recorded the sound.
Should be my voice the whole way through.
We are proving that theorem. The proof goes in 4 lemmas. We've done 1.
Yeah.
So we still need to do 3, which is a lot. And I don't understand the lot. So I'll stop before the lot. No, I kind of understand.
It's stuck on me.
Yeah, so the first lemma was that if you have a finite abelian group and P is a prime number that divides the order of the group, then there is an element of order P. Yeah. Maybe not. Yeah, it's not true, so P is not a prime, and it's not true. You don't always get. It's not enough. It's a divisor of the order, you don't always get up. But if it's a prime, then we proved it for abelian groups, and later we will monoabelian. So that was 13.6. Now 13.7 is a number. Oh, we should do this one.
Not in a box.
Not yet. Yes. Box. Okay. And says that a finite abelian group G is a P group denominator. The order of G is a power of T. That's a lemma. So remember the definition was G is a P group. What was the definition?
He was a P group if
The order of every element is a power of P.
every element in G order was P, or a power of P.
Yeah. The order of every element.
Jesuit.
Alright.
My handwriting.
Oh my god.
Yeah, you see.
Stop, is it all right?
Give it a whack.
Where?
Oh, not there. No, that made it worse.
Okay.
Oh.
Leave it.
No, it makes it worse from the top, so it makes it better. That makes sense. Yeah, so that was the definition. Now the lemma says that the order, so we don't have to look at every element, you just count them. If it's a power of P, it's a P group. If it's not a power of P, it's not a P group. Kind of easy. So, I mean, that is not very hard to prove because it just goes from 13.6 almost directly. So, so which way do you want to do first? If the order of G is a power of P, then the order of every element is what can it be? The order of F of an element always divides the order of the group by Lagrange's theorem. So this direction we do monitor. So the power of E divides the order of the group by Lagrange's theorem. Okay? The other direction is from number 13.6, because if you have a P group, okay, so every element has all the power of P. So if the order of G is not power of P, it's divisible by another prime. Okay. Well, P. And by the previous lemma, G has an element called U, which is not power. Okay.
What do you want?
I
What's
want-
the box?
oh,
No, you want that. That's what I want.
What's the box?
Stealing my food.
Should have had tea and sort of all
I'll buy you a salad afterwards.
It's not the same meal.
about them.
Is that clear? So that's two. Two down, two to go.
We proved that very quickly.
The print itself doesn't.
Yeah, I know, but if he doesn't want to put his full.
We'll just finish it.
That'll take an hour just to write the statement. Okay. So we're still dealing with finite abelian groups. Now, we know what P groups look like, right? Kind of. Don't know what P groups look like yet, but we know that P groups have all elements are have order power of P, and the group also has power of P, and that's equivalent, and so on. So now, what if the order is not? What if the order is not a power of a prime? Well, if it's not a power of a prime, then it's the product of powers of primes, because every number is the product of powers of primes. So it has to be some P1 to alpha 1, Pn to n, k, over k. Okay, and that's point 1. That's so these PIs are distinct primes. and these alphas positive integers. Not listing the primes that don't actually exist. Now, in this case, to prove that, G is the direct product of some P. And G is the internal direct product of subgroups G1, and each of these subgroups consists exactly of the elements whose power, order is a power of that corresponding value. Okay, so each of these subgroups is a subgroup consisting of the elements whose order is a power of P. That's the lemma. Did it say that? Stop. Where is stop? Set stop. Let's stop. What is the internal direct product?
I was wondering now.
We talked about it.
That was
Direct
the
product.
so the internal direct product.
I don't even know what's direct product no matter. So you can
What's what?
direct product.
Yeah, you don't need it for this one.
Yeah, but we need to know what would be.
No, not for this one. You
Not
need
for
to
this
know
one.
it in general, yes, but not for this lemma.
Right, okay. So what is internal direct?
Okay, it's on page 160,
No, that doesn't make sense.
which is 2 months ago. Okay,
I don't remember that.
but for two subgroups, the internal direct product is, well, you have two subgroups in G, or H and K. They only share the identity. Everything else is the product of one element in H and one element in K. And these products commute. So if you take something from from the left subgroup and something from the right subgroup, no matter which way you multiply them, you get the same. Okay? And then there was a theorem that if that is true, then the group is isomorphic to the usual direct product of H and K. Okay, that's the definition.
No, I didn't really follow that. Sorry.
What's
Oh, that's not
direct
my
product?
Okay. Yeah, you can kind of separate the group into two.
Yeah.
Which are very independent. They're independent in the sense that they only share the identity. Well, they have to share the identity. And timesing them one way or another doesn't change anything. And the split means that when you take, you get the whole group when you put them back together. And there's nothing left unexplained. Stay there.
When you say when you put them back together? What? You mean when you just join the two?
Okay, so
I'm like,
Gillian did this with you lot. So if you take an external direct product, it's an internal direct product. So for example, if you take Z3 times Z3, what are its elements? Well, AB, A is in Z3, B is in Z3. Now this has two subgroups. H, which only just A and 0, okay, and A is in 0. That's a subgroup. You only take all the elements that have a 0 on the right. Yeah? In fact, whatever the Z doesn't be subgroup. Yeah. Then it's specific, and then you look at another subgroup. And that's where the first entry is 0 and the second one comes. Now that satisfies. What do they have in common? Only the 0, 0. When you multiply them, well, it's abelian, so that is kind of a void condition in this case. But that is only interesting for non-abelian G. And they give you everything, because if I want something that has an A and something that has a B, I take something that has an A and 0 and add to it something that has a 0 and something that has a B. Okay, that's an example. Within this group, these two are an internal direct product. Wasting the time, she says. Now the interesting thing is actually, yeah, 161 is if you want more than two groups, what we have GI to GK. Again, you want the whole group to be the product of the elements in the individual subgroups. You want them to commute, which we have because we're only dealing with an abelian group, so we don't. So this is automatic. And this condition means that that any two subgroups So when you look at an element of one of them, unless it's the identity, it doesn't appear in any other. Okay, so when you take the union of the rest of them, you won't find it there.
What's that?
What's what?
It does explain.
What, this?
Yeah.
Oh no, it's not. It's not what I said. Okay. So this is the independence. What was the independence for two subgroups? It was that the only element they have in common is the identity. Yeah, this is something else. Confusing myself. But yeah, so what is this? When you look at one of the subgroups, say H1, and you take the union of the rest of them. So you look at all the elements that are in H2, H3, all the way to Hn. That's not a subgroup when you take just the union. So you take the subgroup generated by that union, so the smallest subgroup that contains R. And that doesn't to contain anything from H1 or any value of 1.
Is that different?
You know, if
Yes.
you go back to what
Kind
you
of
were
different.
explaining before, direct.
I shouldn't be
direct-
doing this. This has been done before.
What is it exactly?
What is exactly what? It's the definition of an internal direct product, exactly. So so to your question, how is it different from the one before?
Yeah.
Is okay. Yeah, H1. H2. Now, the first condition, if you only have 2 of them, is that if some element A is here, then A is not. Okay. Now, if you have that was just if you have H1, then A here, but A not here, and A not. But also, H is, you cannot get it as the product of something here and something there. Okay? Not only it's not there, but also, moreover, it's not a product of something here and something there. That's what it means. You won't get to the last number. Thank you. Okay, so now we're proving that these things are. So, the first thing we want is that GI is a subgroup. Okay, so we claim all the time that these are subgroups, but why? So Y is when you take all the elements of G whose order is a power of pi, why is that a subgroup? Well, does it have the identity? Yes, because the identity has order 1, which is the 0th power of pi. Now, if G is order pi to be some k, no, not k, it's already used for something R, then what's the order of G inverse?
Say?
It's the same. Because you're getting the exact same subgroup when you look at what G generates, just the cycle goes backwards. So that works. G has order pi and H has order pi, yes, then G. Has order.
Wait, are they the same PI or are they just?
They're the same pi, that's the main idea.
PIs. Or PI, PI.
I R plus S.
PI R plus S would work, but in fact it's PI to the T. The T is the larger of the two. Okay? But that works in an abelian group. So it doesn't work in a non-abelian. Because so I think what you're thinking is, did you say R plus S? R,
Yes, why does it have that order T, where T is the maximum of R?
well, because it doesn't have order T, it has order PI to the T.
So
that is because, so, yes, well, okay, so look at it. Let's kind of,
then GH has order PI. PY.
PI to the power of T.
Yeah, why? Why the order is that?
Okay, why is that? Okay, so so if R is less than S, okay, then G to the PI PI S minus is G to the P yes.
You made it even worse.
So this is E to the PI, and that's E, so it's this. Well, you have to look lower. Yeah, I've made it even worse. So the whole problem with this is that the order is not R, it's PI to the R, so it works differently. It's very confusing. You have to think about it. It's not. Because these things, they don't add, they subtract. For example, for this is this. What you're thinking is, if you take A to the R, times it by A to the S, you get A to the R plus S. Okay? That's very much on your mind. Whereas what we're doing is A to the P to the R times A to the P to the S. Well, that's not A to the P to the R plus S. What it is A to the P to the R plus P to the S. Okay? If you want to do this, if you want to get this, what you're doing is A to the P to the R times A to the P to the R times A to the P to the P to the P to the P to the R. And you have to do this P to the S times. It's kind of, it's much more when you're doing the powers of P that you have to do to get that. That's where all the confusion is coming from. This is what you kind of have. This is what you kind of have wired in your brains, but this is what's actually happening.
Is it P to the power of S and then bottom? What is that?
Yeah, it's P to the power of S. So you have to take that element, P to the power of S times, in order to get that. You're not getting it like that.
Why p to the power of s times rho?
Well, because that's maths.
But it doesn't make sense.
Why not? Because the BC is A to the B to the C. Okay? So if B is P to the R, and C is P to the S.
Can see, yeah.
I'm saying it.
See.
Then this is what you're getting. That's middle school maths. It's just confusing because there's another level of exponent, but that's what's going on there.
What? So,
So it's a subgroup. Don't know what else to do.
I think
Stand in the air.
the
Yeah.
I get the order. I get it being numbers of the two.
Yes.
I think. So that's a way that explains it. It's
Even worse than this.
like almost yes. Unless I'm missing this.
But in any case, I don't want to spend any more time on this. What we were trying to show is that GI, each of the GIs is a subgroup, and it has the identity, it has all inverses, and it's all products, because if you have two elements, each of whose order is a power of P, then their product also has order, which is a power of P. I'm safe, I'm not going to finish. So we've proved that they're subgroups. And so then when you go back to what it looks like, you have to show that no element, so that it's actually, no, we actually have to show two things. Two things. One of them is that when you take an element, each of them, combine them together, you can get everything in the whole group. So anything in the group G can be obtained by taking an element from G1 times an element from G2 times an element from G3 times an element from GK. There's nothing that wouldn't be good. The second thing is they're kind of independent. So each GI, and look at what it shares. J not I and Gj, and the only thing share is the identity. So let's first do the second thing. Save myself stupid i's and j's. I'll assume that I is one because it works the same. It doesn't matter which practice first. This now j goes from 2 to k is just j2 times G2 times G3 GK. So what this gives you is you're taking elements from different G's and you write them in some order, or finite products with elements from the G's. But you can, because it's abelian, you can reshuffle them, so you get all the ones from G2 first, and all the ones from G3 next, and all the ones from G4 next, and so on. So it's just taking one element from G2, one element from G3, one element from GK, putting them all together. Now we want to show that G1 and this terrible thing only share the identity. So let's have a look at something that's in both in G1 and in this G2, G3, GK. Now,
What is that like union that we put before J, GJ? Oh, is that the product? What is it?
what?
You know, between J equal to and K, that notation.
That's the union.
Yeah, union. So what does that do here? Because you say
There's a union.
the union of elements in group G. Yeah? Is that what it does?
It takes all the G's whose index is between 2 and K and does the union. So, because G is in G1, the order of G is a power of E1. That was what G1 was defined like. Yeah. But because G is in the product of G2, G3, GK, G is some G2 times some G3 times some GK. Where each of them has order a power of P2, a power of P3, a power of PK.
Oh. I mean,
So now I'm doing G 2D E2 alpha 2 times P3 alpha 3 PK is the That's because G2 to the P2 to the alpha 2 is the identity. G3 to the P3 to the So yeah. Okay. Don't worry, we've not covered anything substantial. Why is that? Well, because the order of G2 is a power of P2, and it cannot be a larger power than alpha 2 because that alpha 2 is coming from the G. So higher order. Otherwise, it wouldn't work out because it has to be a divisor of the order of G. Okay, so we have these. Now, So the order of G. Divides this horrendous into k to the other. Okay, yeah, I understood. Okay, that's it. Yeah, well, if you do G to the whole thing, it's the identity, so its order is not necessarily this, but it has to be a divisor of this. That's how it works in cyclic groups. And at the same time, G is a power of P1. So the order of G is a divisor of this, and it's a power of another prime. So what kind of power of P1 can divide that product of powers of primes? Zero power, yeah. So that's this. You agree?
Yeah.
So it'll have to be done next week. Thank you for your cooperation. We didn't get to solve them up, and I'll understand it better. Yeah. So the plan is for Thursday.
Was it still you have?
Hopefully still being brilliant. So on Thursday, the tutorial is now at
10.
10 o'clock.
Does the plan for it involve changing them to later?
No.
Like the start time or the end time?
Both at the same distance.
I was being an idiot when I said the book. When I said that the book explains the powers things, it was
Does it explain it better than I do?
it doesn't really fully explain it properly, but I was misunderstanding the way it says it. I was basically just forgetting that, like,